It's worth pausing on how these two poles are being monitored, because the confidence behind these numbers matters. Both the Arctic and Antarctic sea ice RECO-RDs rely on passive microwave satellite instruments that have been continuously operating since 1979, giving scientists an unbroken 47-year data set that doesn't depend on weather conditions, cloud cover, or the polar darkness that makes, pitiful satellite imagery useless for months at a time. That's part of why these records carry so much weight. This isn't a handful of scattered measurements stitched together. It's a continuous, consistent instrumental record spanning nearly 5 decades, cross-validated by multiple agencies, including NSIDC in the United States, JAXA and NIPR in Japan, and the Met Office and British Antarctic Survey in the UK. When several independently OPA-rated monitoring networks converge on the same conclusion using different satellites and different processing methods, that agreement is itself a form of confirmation. It's one of the reasons scientists were so quick to flag February 2026 as genuinely alarming rather than treating it as noise in the data. It's also worth understanding what a stratospheric polar vortex disruption looks like from the inside, because the mechanics matter for anticipating what might come next. And these disruptions aren't binary on or off events. Meteorologists categorize them on a spectrum M, from a minor warming that barely dents the vortex's strength to a full sudden stratospheric warming event where the vortex either weakens dramatically or physically splits into 2 separate lobes of circulation. A full split event is the more disruptive of the two, because it effectively creates 2 smaller, weaker vortices instead of one strong one, and each of those weaker lobes is far less capable of containing cold air or blocking warm air intrusions. The 2024 Antarctic event involved this kind of severe weakening, and it's exactly why the consequences propagated as far and as forcefully as they did, both into the interior of East Antarctica and outward toward New Zealand and southern Australia. Once a vortex disruption of that severity occurs, the downstream effects on surface weather can persist for weeks, sometimes over a month, as the atmosphere works to reestablish its normal circulation pattern. So why does any of this matter if you don't live in the Arctic or Antarctica? A few components. Sea level is the most widely discussed. The Antarctic ice sheet holds enough water to raise global sea levels by approximately 57 meters if it completely melted, though no scientist believes that's a realistic scenario on any time frame relevant to current planning. The more immediate concern is the marine-based ice sheets of West Antarctica, particularly the Thwaites Glacier, sometimes called the Doomsday Glacier, whose eventual collapse could contribute 3 to 5 meters of sea level rise on its own. The ice sheet helviz that buttress Thwaites and similar glaciers are exactly what warming events and warming oceans most directly affect. When the Antarctic polar vortex fails and atmospheric rivers carry warm, moist air to those ice shelf regions, the consequences, even when temperatures stay below freezing overall, include increased snowfall that refreezes into impermeable ice layers, increased surface melt during marginal events, and the gradual reduction of the mechanical resistance ice shelves provide against the glaciers stacked up behind them. Weather pattern change is the second component. The polar vortex failures described here produce weather impacts thousands of miles from the poles. Arctic amplification, the Arctic warming at roughly twice the global average R8, reduces the temperature gradient between the poles and the mid-latitudes. That reduced gradient weakens the jet stream. A weaker jet stream is more prone to large, slow-moving undulations, the kind of high-amplitude ridge or trough patterns behind the extended heat waves, persistent cold air outbreaks, and stalled rainfall patterns that have become increasingly characteristic of mid-latitude weather in recent years. The same process driving Arctic sea ice decline is also reshaping the atmospheric circulation patterns that determine whether you get a hot August or a cold one, a wet spring or a drought. Ocean heat transport is the third component. The cold, dense water that sinks in the polar oceans drives the global thermohaline circulation, the planetary ocean conveyor belt that distributes heat and nutrients around the world and regulates the climate of the North Atlantic in particular. As Arctic sea ice melts, fresh water enters the North Atlantic and dilutes the saline water that drives this deep circulation. Scientists monitoring the Atlantic meridional overturning circulation have documented a slowdown over recent decades. A significantly weakened AMOC would profoundly change the CLI mate of Western Europe, potentially cooling it substantially even as the rest of the planet keeps warming, and would alter rainfall patterns across Africa, Asia, and the Americas in ways current models are still working to quantify precisely. Let me close with what the scientists themselves are actually saying about the significance of what's happened in 2026. The researchers who published the NPJ Climate and Atmospheric Science e-paper on the 2024 Antarctic winter heat wave in April 2026 through peer review with methodology that's been scrutinized and validated by the broader scientific community, write that events of this character could become up to 20 times more frequent by the end of the century under high emissions. Not 2 times, 20. NASA's January 2026 report on rare stratospheric disturbances documented simultaneous, unusual activity in both polar stratospheres, in terms scientists describe as having few precedents in the observational record. The British Antarctic Survey, reporting on the February 2026 combined global sea ice record, used the phrase very alarming in that kind of language from a research institution whose scientific communications are typically measured and careful, carries real weight. Walt Meyer, the National Snow and Ice Data Center scientist who, back in 2022, first pointed out that the Arctic and Antarctic are opposite seasons, that you don't normally see the north and south melting at the same time, called it definitely an unusual occurrence at the time. He now works in a scientific environment where that unusual occurrence has become a recurring data point rather than a single anomaly. The 2022 event, the 2023 events, the 2024 Antarctic winter heat wave, the 2025 AE and 2026 consecutive Arctic winter maximum records, the February 2026 combined global sea ice record low. What happened at both ends of the planet is not one isolated thing. It's a pattern. And the scientists watching it use words like unprecedented, unexpected, alarming, and concerning, not because they're trying to frighten anyone, but because those are the accurate words for what the data actually shows. Understanding this doesn't require alarm. It requires attention. The ends of the planet are closer than they seem, and what happens there is already changing the weather where you live. It's going to change it more. Stay informed, stay curious, and keep watching what happens as the Arctic heads into its September minimum, because this year's number is going to matter. The 2024 Antarctic winter heat wave began with exactly the kind of polar vortex disruption that's only supposed to happen in the southern hemisphere once every 5 years. In July 2024, the Antarctic polar vortex became distorted and weak-kned. Unusual warming spread through the stratosphere, temperatures rising by more than 15 degrees Celsius in early July, with another surge in early August. The disrupted vortex allowed a persistent high-pressure system to develop over East Antarctica, and that high-pressure system opened a corridor, a pathway through what's NOR, Mali, an impenetrable atmospheric barrier, for what scientists call an atmospheric river, a long, narrow plume of warm, moisture-rich air flowing deep into the Antarctic interior from lower latitudes. That river carried heat from mid-latitude oceans straight into the interior of East Antarctica during the polar winter. The result was the most intense winter heat wave in the 46-year satellite record. The researchers calculated the human contribution to this event directly. Their attribution analysis found that anthropogenic warming, the long-term background warming from greenhouse gas emissions, intensified the event by approximately 0.7 degrees Celsius and more than doubled its probability compared to a world WW. Without human-driven climate change, the event wasn't entirely caused by climate change. The atmospheric dynamics involved, the vortex weakening, the blocking high, the atmospheric river, are natural features of the climate system that occur on their own. But climate change made this natural event stronger and significantly more likely to happen at all. That combination, natural variability amplified by human forced warming, is what the paper's authors are describing when they write that events of this character could become up to 20 times more frequent by the end of the century under high emissions. There's a detail in the 2024 Antarctic disruption that connects directly to weather experienced by people who live nowhere near Antarctica, and it's worth understanding clearly. When the Antarctic polar vortex weakens and lets warm air penetrate the continental interior, the cold air that vortex used to contain doesn't just disappear, it gets pushed outward. The 2024 Antarctic winter heat wave simultaneously pushed massive quantities of freezing polar air northward toward the equator, driving unseasonably cold winter temperatures across the southern hemisphere, including in New Zealand, Australia, and the southern cone of South America. That's the seesaw effect of a polar vortex disruption. The cold air has to go somewhere, and when the vortex fails to contain it at the pole, it spills toward the mid-latitudes of that hemisphere. Communities thousands of miles from Antarctica experienced unusually cold winter conditions in 2024, partly as a direct consequence of the same vortex failure that was simultaneously driving record warmth into East Antarctica's interior. That's the sense in which what happens at the poles matters for everyone who doesn't live there. It isn't just an abstract concern about sea level rise, though that concern is real and significant. It's about the behavior of the atmospheric structures that regulate temperature distribution across the entire planet, the polar vortex. Tex isn't a local phenomenon. It's a planet-scale circulation feature that influences weather from the tropics to the poles. When it fails, when it weakens unexpectedly, when it lets warm air into the polar interior and cold air escape toward the mid-latitudes, the consequences propagate outward. The 2024 Antarctic event hit Australia, Leah, and New Zealand directly. Arctic polar vortex disruptions have plunged Arctic air into the United States repeatedly in recent winters. These aren't two separate stories about ice at opposite ends of the Earth. They're the same story, about the stability of the atmospheric machinery that regulates temperature across the whole planet. Now, to right now, August 2026, because this is the context this video's title draws from directly, the Met Office's Arctic and Antarctic sea ice briefing, published August 2nd, 2026, describes the current state at both poles. In the Arctic, extent on August 2nd sat at 702 million square kilometers, ninth lowest in the satellite record, 1.38 kilometers. Laying square kilometers below the 1981 to 2010 average, with the summer melt season still running and the September minimum still ahead. That September number will be one of the defining data points of the year for understanding where the Arctic stands. The Met Office's July 2026 briefing documented Antarctic sea ice extent at 1470 million square kilometers on July 8th, sixth lowest on record for that point in the year. Extent was particularly low in the Bellingshausen Sea and the western Weddell Sea, adjacent to the Antarctic Peninsula, and somewhat low in the Indian Ocean sector too. The June and July 2026 Southern Ocean has been characterized by a strongly positive southern annular mode, lower than normal pressure over the Southern Ocean near Antarctica, and enhanced westerly winds circling the continent, which the Met Office explicitly links to the El Niño pattern that's been developing through the spring and summer of 2026. That El Niño connection at the Antarctic deserves a moment of its own. The same strong El Niño reshaping weather patterns across the continental United States is also influencing the atmosphere around Antarctica. The pressure patterns and wind circulation anomalies in the Southern Ocean through June and July 2026 are consistent with El Niño's atmospheric signature at high southern latitudes. The interconnection between the tropical Pacific and the polar regions isn't a theoretical construct. It's visible in real time in sea ice and pressure data from both hemispheres simultaneously. Let's talk about the Blue Ocean event, because it's the specific threshold polar scientists have been tracking with particular concern, and the 2026 data at both poles has put it back into sharp focus after February's combined global sea ice record low. A blue ocean event is defined as the moment Arctic sea ice area falls below 1 million square kilometers, essentially. Near total disappearance. The term comes from the visual, an Arctic Ocean where the ice has retreated so far that dark blue water is visible from satellite in nearly every direction, rather than the white of sea ice. At 1 million square kilometers, whatever ice remains is confined to small areas, around the Canadian archipelago and near the North Pole itself. This event has not yet occurred in the 47-year satellite record. The current September minimum record is 3.41 million square kilometers, set in 2012. But the trajectory is clear. Arctic sea ice area has been declining at roughly 12 to 15% per decade in summer. Arctic sea ice volume has been declining even faster than area because the remaining ice keeps thinning. Arctic monitoring groups tracking this data in September 2025 noted the threat of a blue ocean event was growing and flagged the possibility of a double blue ocean event, both poles approaching the 1 million square kilometer threshold in the same year, as a realistic risk for 2026 or the years immediately following. A blue ocean event would be a genuinely significant threshold crossing, not just another data point in a long decline, but a physical event with real consequences. Open Arctic Ocean in September reflects far less solar radiation than sea ice does. The ocean absorbs up to 94% of incoming sunlight, while sea ice reflects 80 to 90% of it back to space. A blue ocean summer would substantially increase the heat absorbed by the Arctic Ocean, accelerating the warming of the entire polar region and triggering feedbacks in permafrost thaw, methane release, and atmospheric circulation that would be difficult to reverse on any timescale relevant to human planning. The 2026 season hasn't produced a blue ocean event. The September minimum is still ahead, and whether it approaches record lows or stays within the recent post-2007 range depends heavily on specific wind patterns over the Arctic Ocean through August and September. But the February combined global sea ice record low, the second consecutive Arctic winter maximum record, the currently below average Antarctic sea ice extent, and in the publication of the peer-reviewed paper on the 2024 Antarctic winter heatwave together constitute, in the language of the scientists monitoring these systems, something that was not expected to happen this quickly. In February of this year, something happened that had never happened before in the history of modern Earth observation. Scientists measuring the combined area of sea ice covering the Arctic Ocean and the waters around Antarctica calculated that total global sea ice extent had fallen to 15.76 million square kilometers. That number is a record. The previous lowest combined global sea ice extent on record was 15.93 million square kilometers, measured in January 2023. February 2026 beat it. Total sea ice across both poles simultaneously reached its lowest level ever recorded in the 47-year history of satellite monitoring of both ends of the planet. Less ice than we have ever seen at both poles at the same time. The British Antarctic Survey, one of the world's leading polar research institutions, was direct in its assessment, calling the simultaneous records very alarming. Here's what just happened at both ends of the planet and why it matters for everyone who doesn't live at either pole. What made this more than just another data point in a long trend line of decreasing polar ice is a simple fact scientists kept returning to. The Arctic and the Antarctic do not normally melt at the same time. They're opposite seasons, opposite hemispheres. When one is in winter and growing ice, the other is in summer and losing it. That's the normal rhythm the planet has run on for as long as we've been measuring it by satellite. When both are simultaneously showing record or near record low ice coverage, something has gone wrong with the rhythm itself. Scientists at both poles have spent 2026 trying to understand exactly what. What they found is more complex, and in some ways more alarming, than a simple story about warming oceans would suggest. It involves atmospheric structures in the stratosphere, miles above the surface at both poles, that are supposed to act as refrigerators for the polar regions. Those structures have been failing in ways scientists describe repeatedly and with evident concern as unexpected. Start with the Arctic, because the data from March 2026 is where this dual polar story begins. On March 7th, 2026, Arctic sea ice reached its annual maximum extent, the point where the Arctic Ocean's ice cover peaks for the year before spring and summer melting takes over. That maximum reached 1434 million square kilometers. Here's the context that number needs. The 1981 to 2010 average Arctic winter maximum extent was 15.65 million square kilometers. The 2026 maximum came in at 1434 million. That's 1.31 million SQ. Were kilometers of ice that simply wasn't there. Not below some theoretical maximum, not below a pre-industrial baseline, but below the average that existed within recent decades, the period as scientists actually use as the modern reference. To visualize 1.31 million square kilometers, that's approximately the size of South Africa. An area the size of South Africa's worth of Arctic sea ice was missing this winter compared to what was typical through the 1980s, 90s, and 2000s. The National Institute of Polar Research in Japan and the Japan Aerospace Exploration Agency, which jointly maintain one of the world's most detailed long-term satellite sea ice datasets, confirmed that the 2026 Arctic winter sea ice maximum was the lowest value since satellite observations began in 1979. March 2025 had set the previous record low. March 2026 matched it within statistical rounding. 2 consecutive years holding the lowest Arctic winter sea ice. Extent were recorded. The British Antarctic Survey put it plainly. 1.3 million square kilometers of Arctic sea ice is missing in action in 2026, and what's still there is thinner than it used to be, following what they called a worrying long-term downward trend. Extent, the area covered, is one met, sure. Volume, the actual amount of ice accounting for both area and thickness, is another. And Arctic sea ice volume had been sitting at record daily low levels for more than a year through the September 2025 annual minimum. The ice that exists isn't just smaller in area, it's shallower, younger, more vulnerable to summer melt. The most recent Met Office Polar Sea Ice Briefing, published August 2nd of this year, shows Arctic sea ice extent at 7.02 million square kilometers as of that date. Ninth lowest in the satellite record, 1.38 million square kilometers below the 1981 to 2010 average. The summer melt season is still ongoing. September, the month of the annual minimum, is still ahead, and it's one of the key data points that will define where 2026 lands in the broader record. Now to Antarctica, because this is where the story stops, being simply another sea ice statistic, and where scientists didn't expect this becomes precisely accurate. In July and August of 2024, East Antarctica experienced what a peer-reviewed study published in the journal NPJ Climate and Atmospheric Science in April 2026 described as the most intense winter heat wave in the 46-year satellite era. Stop on the word winter for a secco. Onanagar, July and August in Antarctica is the dead of winter, the deep polar night, months of total darkness, temperatures routinely below minus 30 degrees Celsius, the continent at its coldest and most inhospitable. This is the season furthest from any possibility of melting. There is genuinely no sunlight reaching most of the continent during this stretch. During that winter darkness in 2024, temperatures in parts of East Antarctica, in a region called Drawning Maudland, rose to 9 degrees Celsius above the climatological average and stayed there for 17 consecutive days. 17-day S in the dead of Antarctic winter, more than 9 degrees above what's normal. And it wasn't just a modest temperature anomaly. Some areas experienced warming of up to 28 degrees Celsius above average in July 2024 during the Antarctic polar night, with no sunlight involved at all. The researchers behind the NPJ paper spent years working out the mechanism. What they found was a pronounced weakening of the stratospheric polar vortex that set off a chain of events leading directly to that unprecedented surface warming. The polar vortex is the mechanism at the center of everything happening at both poles right now, and it's the structure scientists did not expect to fail the way it's been failing. It's a band of very strong, fast-moving winds that circulates around each pole in the stratosphere, the layer of atmosphere roughly 10 to 50 kilometers above the surface. In the Arctic, it spins counterclockwise around the North Pole. In the Antarctic, clockwise around the South Pole. When the polar vortex is strong and intact, it acts as a refrigerator lid for the polar region, keeping extreme cold air locked in place, preventing it from escaping toward the mid-latitudes and PR, preventing warm air from flowing in from outside. When the vortex weakens or disrupts, the consequences are dramatic and immediate. Cold polar air escapes toward the mid-latitudes. This is exactly what produces the polar vortex disruption events that have sent Arctic air plunging into Texas and the eastern United States in recent winters. And simultaneously, when the lid breaks, warm air from lower latitudes pushes into the polar region instead. In the northern hemisphere, the polar vortex undergoes what meteorologists call a sudden stratospheric warming event roughly once a year on average. NASA's January 2026 report on rare stratospheric disturbances documented this frequency explicitly. The northern hemisphere's complex terrain, the Himalayas, the Rockies, the Andes, regularly generates atmospheric waves strong enough to weaken or split the Arctic polar vortex. The Antarctic polar vortex is normally far more stable. NASA's report is explicit on this point. 2. Sudden warming events happen in the Antarctic only about once every 5 years, far less often than in the Arctic, because the southern hemisphere has fewer large mountain ranges and continental land masses to generate the wave activity that disrupts a polar vortex. Antarctica sits in the middle of a vast ocean, and the atmospheric flow around it is characteristically more symmetric and stable, or at least it used to be.